Let's get going here. How was the assignment? Good, bad, awful, too hard, too easy, too long? All right. So the plan is I'm going to put out a practice final exam like the practice midterm, hopefully before the weekend, but by the weekend we'll have a practice final exam. We'll put out a solution to that sometime the middle of next week, and then we'll have a review session, which isn't really a review session, but we'll answer any questions that people have, and I'll put out a doodle poll on that so that people can vote on what time it is. Okay, and that will be on Piazza, and I'll post that on the weekend too. Okay, so it'll be sometime in the couple of days before the exam, probably on the Friday or the Monday before the exam. What else do I need to... Any questions about anything? Unlike in the midterm, you're allowed to bring in one sheet of paper with anything written on it. It's not an exam where you memorize things, it's an exam where you show what you've learned. And if you've done all the assignments and the clicker questions, you shouldn't have any trouble with it. It's not meant to be tricky. Okay, any questions about anything? All right. So last time we did this, and last time we did this variable elimination to find an optimal policy, or what's called dynamic, essentially the original dynamic programming algorithm. We create a factor for each conditional probability. We repeat, we sum out a variable that's not a parent of a decision node. And before there was a confusing paragraph, but I rewrote the paragraph now in the middle. Is once you've summed out the random variables that are not parent of decision node, there'll be some factor f that contains d and some other nodes which are parents of d. This always happens if you have a no-forgetting influence diagram. You always get some variable d and some other variables in this factor that are parents of d. And if you keep in, this is going to be the last decision that we're going to look at, the last decision. We're then going to eliminate d by maximizing. This returns both an optimal decision function, which we write as argmax, with the value that maximizes, and a new factor. I'm going to keep repeating this until there are no more decision nodes. So once you've done that. We're going to sum out the remaining variable, and this is the expected value of the optimal policy. Okay, are there any questions about that? That's what we went through last time. Okay. And then at the end of last time, we did the value of information. Information x for decision d is the utility of the network with arc from x to d, plus any no-forgetting arcs. We need those no-forgetting arcs for this algorithm to work, minus the utility of the network without the arc. So you add an arc, and then you're going to subtract it from there. The value of information is always non-negative. If you have more information, you can always make a better decision because your previous decisions are always available to you. So the things you could have decided to before are still available to you, but you just have more options. So you can always do better. Assuming this model of perfect rationality, as soon as you get to bounded rationalities, it's hard to think about things, this is no longer true. And if you get to multiple agents, this is no longer true. Right? So it's only in this assumption here of this perfect rationality in single agents, this value of information is always valuable. It's always useful to you. And if the value of information is positive, the reason you gain information is because you do something different. You do something differently. So if the value of information is positive, the agent must change its action depending on x in the optimal policy. Okay, any questions about that? All right. Let's go to some clicker questions. Basically, so you'll know this because you didn't ask any questions. So in optimizing, after summing out some variables, which decision node is maximized first? This is the one we've seen before. All right. How are we going? Does anyone need more time? 3, 2, 1. Oh. Just the answer is call. Because what we're going to do is we're going to sum out. Let's look at this. The answer is call, which is A, I think. The answer is call. We're going to sum out all of these variables. So which variables we're going to sum out? We're going to sum out tampering, fire, alarm, smoke, and leaving. And we'd end up here in a factor that contains call, see smoke, check smoke, and report. And let's go to this one. And we end up here with this factor F, where D is the decision node and all the others are parents of it. So there's two choices in here. There's call. Are all of these parents of call? Yes, right? So this is see smoke, check smoke, and report are all parents of call. The other alternative is check smoke, and are all of these other variables parents of check smoke? No. Okay? Call and see smoke are not parents. We can't optimize check smoke first because we can't implement check smoke. Do we check smoke based on whether we see smoke or not? Well, if you going to see smoke, then maybe we shouldn't check because checking is expensive or something like that. We can't have a test that depends on something in the future. We can't decide to do something knowing about something in the future. So the answer here is call. It's the only one that follows this definition. Okay, so the answer is call. We do the last decision. We're going to optimize the last decision first. We're going to go backwards from the future, just like we did in regression planning. We're going to go backwards from the future. Any questions about that? Okay. Oh. I won't do that. I'm lost. There. All right. We'll do that. Adding an arc from tampering to call. So we're going to add an arc from tampering to call and optimizing. A, requires new initial factors to be defined. B, can decrease the expected utility of the optimal plan. C, can change the decision function for check smoke. Or D, cannot change the expected utility for the optimal policy. How are we going? Does anyone need more time? Anybody need more time? Let's, here we go. 3, 2, 1, we'll stop. All right. All right, let's play. So A, B, C, D. Adding arcs parents to decision nodes doesn't require new initial factors. In fact, if I go to here, I can just add it. I can just create a new factor and I can optimize. There's no new factors. There's only factors for random variables and utility. There's no factors. There's no initial factors for the call function. Okay, so I can just add this with it, and I don't need to define any new factors. Okay, so A is wrong. So A is wrong. So that's what's the other one? I'm lost. Wait a minute. I'll go to here. So can it decrease the expected utility of the optimal plan? Well, we now have more information available to us. Everything that was available to us before is still available. So B is wrong. We can't, if we add tampering, we now can do more things than we could before. We have more options available to us. It can't decrease the optimal plan. These were all on the previous slides, right? D, it cannot change the expected utility optimal policy. Well, it can change the expected utility optimal policy, so then we were left to wonder about C. So the other ones we've been told about, and C seems implausible, but let's have a look. Let's see what happens. Let's go there. So let's delete this arc, and we'll go to solve mode, and we'll optimize decisions. And we'll do it briefly, means it's not going to ask all these questions. And the expected utility, the initial one is minus 22.6. So initially is minus 22.6. And the policy for check smoke, and if I view and modify this decision, the policy for check smoke, if you look over on the far left there, says I should check smoke if there's a report, otherwise I don't check. So for check smoke, it says I should, if there's a report, if report is true, then check is true, then check, else don't check. Okay? So let's know to OK. Now I'm going to go back to here, and I'm going to create an arc to there, to tampering. Now I'm going to optimize, go back to solve mode, and I'm going to optimize my decisions, and it's going to remove all my functions. And now I'm going to do this in brief mode, and it's minus 22.3 or something, minus 21.3. So after there's the arc from tampering to call, it's minus 21.3. So it did improve the utility. And let's look at this decision. Let's look for check smoke here. Why isn't that letting me do that? Oh, hang on, what's happened here? And if I look at this, I never check. So it turns out that I never check for smoke here. The policy is never check for smoke. And the reason we're doing this, the reason we're not checking for smoke is expensive. And if we look at what the policy for call is, if we look at this policy, well, we're never going to check for smoke. So, but notice here we have this policy here for every check smoke and every see smoke. But we don't check for smoke and we don't see for smoke. So the only things we want to look at here are both the false, the two right on the false. So what's going on here? So let's look at the two with the false right. So there's this one here which says that if there's tampering and there's a report, I don't call. So if there's tampering and I don't call then. If, let's look at false, false down there. If it's, I don't call if there's tampering and there's no report. And I do call if there is no tampering and report, and I don't call if there's no tampering and no reports. The only time I call is if there's a report and no tampering. Right, so the only time I call, so I call, in this case, if there is tampering, if there's report and no tampering. And it's not worthwhile checking for smoke. Because once you know at this stage, at the latter stage, you know whether there's tampering. You know, we know that basically a false. If there's tampering, it's undoubtedly a false alarm. It's not worthwhile checking for smoke. Okay, any questions about that? This is the sort of thing you can just work out from playing with this, working out what the optimal decisions are here. Okay, any questions? Okay, where am I there? So next question. Isn't as tricky as the previous one. Oh, hang on. I think this one. Adding an arc from tampering to call and optimizing changes the expected of utility. Therefore, what must happen? The decision function for call does not depend on tampering. The agent does different actions when calling in some circumstances. Or adding an arc from tampering to check smoke cannot change the utility again. How are we going? Does anyone need more time? Of course, different here means before we've added the arc and after we added the arc. Okay, does anyone need more time? No. All right. Yes. B is right. Some of the times we're doing different things just to check to make sure, because it has to do different things. If we have an increase in utility, we have to do different things. We only get utility from our actions. Right? It's sort of this very legalistic thing that says the only thing we get rewarded for is what we do, not what we think. Right? We get rewarded here for our actions. Right? The fact that we can think about other things doesn't help.
So would it be better to say make different decisions regarding calling? Because this sounds like he does something different when he calls whoever is calling. It's kind of strange wording, I think.
No, in some circumstance, it actually calls different. So if there is tampering and there is a report and it sees smoke, it does something different. It doesn't call when it does call.
Right, so it's a different decision. It decides to call or it doesn't. Is that weird?
It does different actions. Yes, the action is different. It calls instead of not calling. You don't like that wording, Zoe?
Yeah, no, but whatever. It's fine.
It does different things. It acts differently. It does different actions. Its actions are different.
It sounds like it's calling someone different, which is not really.
Well, one time if report is true and see smoke is true and tampering is true, originally it calls and later, and then after the arc is added, it doesn't call.
Yeah, I guess the wording is only when it is decided to call. That's fine.
Yeah.
If tampering is connected to the call, how can tampering connected to check smoke affect the utility?
Well, let's do it. All right, let's add this. Create an arc from tampering to check smoke. Whoops. Create an arc, tampering to check smoke, and I solve it, and I optimize my decisions. Oh, and this says I delete all my things. We want to do that. And I do brief mode because I don't want to get into that other thing. It's minus 20.8. So after both arcs, so there's now an arc from tampering to check and call, to both check and to call, right? There's an arc to both of them. Tampering to both check and to call, we get better. So it's better than this. So it's minus 20.85. And if you noticed how the algorithm works, you notice that exactly the same thing happens for call. So the call function does not change, right? Because we optimize call based on all of these other things. We didn't know what we're going to do, whether we're going to check for smoke. We just essentially looked at all the combinations for checking on smoke or not. So the only thing that could change is the policy for checking smoke. And if we look at this one, we'll find that it must, of course, change. And it does. So if tampering is true, it's going to check for smoke, and if tampering is false, it's not. So if it knows that there's tampering, it's going to ignore the report. And if it knows there's tampering, it's going to check for smoke. Right? Right, so here the policy for, it's going to do something different when checking for smoke. So it's going to check for smoke if and only if there's tampering. Okay, does that make sense? And it's interesting going backwards through these. What's important is when we did call, we essentially did all these combinations for tampering, report, and checking smoke. And we sort of, what would we do in all these circumstances? And that lets us then optimize this decision independently. Okay, any questions about that? Why? Well, because your alarm's unreliable. Someone's been tampering with your alarm, you know that your sensing mechanism's all wrong, right? If someone tells you that all the alarms have been disabled, you should really be careful about smoke. Whereas if your alarm works, right, then you don't have to worry about smoke because you can get a report. Right? Does that make sense? It's not that silly. It's all contrived, of course, because it's all designed to give. All right. Okay. All right. So what we're going to do for the next, where am I here? What we're going to do for the rest of the week is we're going to play with some belief and decision networks for learning, localization, and natural language. So really what we're not going to do any new algorithms. All we're going to do is to show some applications of these belief networks and other things, and decision networks for learning, localization, natural language. We'll tell you how Google works and all sorts of things. So at the end of the class, you should be able to talk about learning probabilities, constructing something called a Markov chain, and we're going to talk about then using what's called a hidden Markov model for localization. All right. So first of all, we're going to look at where the probabilities come from. So far, we've just assumed all these probabilities are just given to us, but they come from both experts, people who know, and from data. And so let's give an example. We're going to assume we're going to have a thumbtack. I'm going to have a thumbtack here. I have a thumbtack. Doc. I have a thumbtack here. It's here. It's there. It's in two positions. This is position heads, and this is position what we call tails. So it has the point up. Can you see that? So if I toss it, you can see. All right. And we're going to have n0 instances of heads is false, and n1 instances of heads is true. So we're going to have some data. And the question is, what should we use as the probability of heads? What's the obvious answer? Well, no, we have data. We've observed data. Yeah. Right, so the obvious answer is you're going to do what's called the empirical frequency of n1 divided by n0 plus n1. All right, does this seem obvious? Does this seem obvious to everyone? Right, this is the wrong answer. You don't want to do this. We'll tell you why. There's another answer in 1812. Laplace said we should add one to, we should use n1 plus 1 divided by n0 plus n1 plus 2. This works when n1 and n2 are 0. It works if you just have very small counts. And so Laplace said this is the right answer, and he answered the question, what probability should you do for the sun rising? Well, it depends on how many days you've seen the sun rising, and you've got to do this. So that was one of his arguments, and we'll see why. So he said you shouldn't use this number. You should do. You should add 1 to it. But the other thing you can do is you can have what are called informed priors. Is you can have. You don't have to use 1 and 2. You could use some other counts that sort of some expert gives you. Some experts can give you pseudo data, and you can add those to N1 and N0. Some what we call pseudo counts is some experts are going to tell us things, and we can apply it, add it to data. And we'll use that as an example. And we're going to claim that 1 and 1 express ignorance, that in fact Laplace is what we should use if we're ignorant about things. And this is a problem called, basically the empirical frequency does what's called overfitting the data. Okay, so here's an example of doing something. So here's an example that, so we have a website where people can rate restaurants with 1 to 5 stars. Right, so each restaurant has 1 to 5 stars. And you want to report the most popular restaurant. Right, we just want to say, what's the most popular restaurant in our database? And how do we determine the most popular restaurant? Which one is it? What's it? Well, no, that just has. Right, so right, you could have most, but I mean the highest average, we're the best rated, the one with the highest average rating, right? Sort of obviously the highest average rating. So the question is the restaurant with the highest average rating the most popular restaurant? Well, even in popular, it has this thing. So which one has, right? Oh, well, we wanted the highest average rating. So the question is, which restaurants have the highest average rating? Right, someone with the ones get this right. So in fact, what happens is that the ones with the highest rating are those ones with very few reviews. Right, so in fact, it turns out that they have a rating of 5, and the restaurants with a rating of 5 are those with very few reviews. Right, no matter how good you are, if you have lots of reviews, you will not have a rating of 5. The most popular restaurant will be the rating with just 1 5. Right, and this sort of overfits the data. We have very small amounts of data in there, and now we want to overfit this data. Okay, and there's all sorts of solutions you can do, but you can follow from Laplace. Is what we do is we basically start off with giving every restaurant some average ratings, and then you've got to get enough ratings to increase your policy. Okay, so if you're trying to do this, here's an obvious case of where overfitting arises. So you don't just average in your restaurants, you actually start off with some average ratings, and then you keep adding in the real ratings, and they've got to keep boosting themselves up. They've got to keep getting good ratings in order to get to the top. So things are going to filter their way to the top. So overfitting happens when we have few data sets, and we try and fit to those few data sets. Okay, so all right, so at least we're convinced that maybe that overfitting happens. So so because we have Bayes nets, and we like Bayes nets because they're fun things, let's solve this problem with Bayesian networks. So what we're going to do is we're going to say there's tosses, and whether it's heads or tails depends on the probability of heads. Right? So whether toss 1 is heads or tails depends on the probability of heads and is independent of the other ones. Whether toss 2 is so you all know what this Bayes net means. It means the tosses are independent of each other given the probability. And so now we have the probability of heads is a random variable representing the probability of heads. So this is the probability of heads, and its range here is is either some discrete set of 0.1 or a real interval. And then the probability of the toss of the head of n is heads, given the probability of heads is v. What's this probability should be? You have a random variable called the probability of heads. What should the probability that toss n is heads, given the probability of heads is v? What should that be? What should it be? Come on. We have a variable. We know the probability of heads. We're given the probability of heads. What's the probability of heads? Oh, V, right? So this should be V. This is actually in statistics, they call this the IID assumption, the independent and identically distributed function. It says they're independent of each other given this. So let's go through, let's look at this, this thing. Copy this. Oh, hang on, I have to copy the whole thing. Oh, well. I'll copy this. If I click on that, I get to this, and I go to here, and I view, load from URL, and it's just the normal way, and you know how. All right. And it says BayesNet. It's actually the one, there's actually a whole lot of tosses underneath here, by the way. So I'm going to, whoops. So I'm going to have, there's tosses underneath here. What I want to do is I want to monitor, the probability of heads here is this 11 valued random variable has a probability of 0.05, and it's exactly the algorithm we've seen before. There's nothing hidden here. There's only hiddens of these things. And what I'm going to do is to predict the toss 11. All right, now we're going to make observations of this. And if you look at what the conditional probabilities are, this is just the prior on this, and we're going to have, view the probability table for this is going to be what you'd expect. Right, the probability of toss here is 11 exactly corresponds to the probability of heads. And we don't remember what heads and tails are now, do we? So, and if you remember what we did before was, just to make sure that we're consistent, is this is tails. And this is heads, this is tails, and this one was heads, was on the side, right? Okay. So let's do this. Oh, let's put this back on the webcam, .cam. Let's do this. I don't know what this is going to do. We're going to toss it once, and it's tails. Right, so we're going to observe toss 1 to be tails. Make an observation. What's going to happen? Make an observation to be tails. Oh, and now we're going to try, now the idea is what do you want to expect the prediction of toss 11 to be? Right, so if we do this, what's going to be? Can anyone guess? It's going to be lower, it's going to be 0.33. It's going to be 1/3. Okay? Maybe Laplace was right. That's what he predicted a long time ago, and it agrees with my BayesNet. So let's create another toss. Let's do another toss. And it arrived at, oh, can you see that? It's tails again. What's it going to be? Oh, be precise. Come on. Make a prediction. So, oh, let's draw this. We got, with 0 it was a half. When we did one tail, it was 0.33. If we did, now we've got 2 tails. All right, let's try it. 0.25. Right, this is actually 1/3. This is 1/4. And if we keep going, oh, tails again. Oh, sorry. Actually, we've got to move this thing, don't we? Let's move this there and this there, and we'll anticipate all my future tosses. We'll do a few there. And we make an observation of I'm lost. Make an observation. There it is. And do this to be tails again. And it's going to be 0.19. Three tails is... What was that? It's not fair. In fact, this is nice because we don't know what it's like, right? You don't have strong prior expectations of what it is, right? So that's why we're going to use this as heads and tails. Ah, good. I got a heads. Heads. And it gets to be 0.34. So this is about 1/5. And this was about 3 tails and 1 head was about 0.34, which is about 2/6. And if I discretize this into not just 10 bins, but 100 bins or 1,000 bins, as I discretize it more and more, I get exactly what Laplace suggested. Okay, does that make sense? Questions about that? So once you've seen the Bayes net, you know what the conditional probability is, you know how to implement it, you know what it means, right? We know how to implement it, we know what it means, it's just exactly the same thing that we did before. All right. Where am I there? All right, questions about? Okay. So now we can think about doing the same thing as this request before we did this help system. But now we know how to learn things. We now know to use data and prior expert knowledge. So what do we need to do this? What probabilities do we need? It's the same question we always have. They're all the same. Right, we need the probability for each help page and the probability for each word given each help page. This is the probability of each help page, and the probability of each word given the help page. Each word given the help page. All right, so these are the probabilities that are required. What counts are we doing? Right, we're just going to have the count of the number of times each word appears, is used for each help page, and the count for each help page. Right? So we're going to have the number of times HI is used is the correct web page, and the number of times WJ was used in the query when HI was the correct web page. I'm just going to do this just by normalizing. And this one here, for every web page, we're just going to have this probability we're going to do before. Right, so that was what we did there. Did I change notation? Oh, that's fine. I swapped I and J, that's okay. So now we do this thing here as when can you update the counts? So now we're going to use this system and it's going to learn. When do we update the counts? After each word you can update the count, can you? What do you know then? You have to know these counts. When do we know these counts? You don't know them after each word because you don't know when they type in a word what the help page is. So when do we learn? When do we do this? When do we update? When do we learn? When do we update our counts? Right, when the user's found the help page they're looking for. Does that make sense? When the user's found the help page they're looking for, we can update these counts. If the user never finds the help page they're looking for, we can't update them. And so this is the reason why Microsoft asks you, is this the correct page or not? Because then it can update the counts. And the funniest thing is, you think it says no, it learns, but in fact it knows by saying yes. It probably throws out, or it used to throw out no's. Right? When it's learning, it only knows, if this is the model it used to be, only used it when it found the correct page. If you found the incorrect page, it didn't know what to do. Right? It didn't actually learn from that. So it updates the counts when it finds the correct page. So what prior counts do I do? Right, so when I first bring in the system, it learns. I want it to learn, but I have to make it work before it starts. Right? I don't want to why do I use zero probabilities? No, if I use zero probabilities, it means as soon as someone uses this word, the probability that help page is 0. Right? So 0 probabilities multiplied in end up being zeros. So I don't want to use 0 probabilities, and I make up some things, and I make up initial counts, presumably based on common words and what words are actually in the help page. Or if it's about printing, I expect printing to appear in it. So I'm going to start it with that. But that's not very good information. I'd much rather know what queries do people actually use. Okay. So I'm not going to answer any of these questions. So if we're designing a help system, there are lots of issues that arise. So what if the most likely page isn't the correct page? It actually learns wrong things. So if it keeps finding the wrong page for you, it's going to keep thinking that's the right page, and it's going to get off track. It's going to learn the wrong thing. So it's going to find out things that are wrong. If the user can't find the correct page, it actually does nothing. It doesn't learn from its failures, this particular algorithm. It only uses these particular models. It doesn't. If the user can't find the correct page, it doesn't actually update any of these counts. It's only from the correct page. If the user mistakenly thinks they have the correct page, then right, so if the user thinks they have the correct page, it actually learns and says, oh, it's right. And so it then goes off and makes and sort of updates its things it's learned about what's going on. So there's other so if one of the problems that some pages can never be found if they're essentially dominated by other pages. We can never find that particular page because it ends up having a lower probability, and then the probability keeps dropping. So it becomes less and less likely that people think that's the right page. One of the problems with these is common words. You end up having to model those separately. We end up having very common words like it and thee. We often just ignore them because they don't tell us much information. The only ones that we really need is those ones that really help to discriminate the help pages. Right, so common words you ignore. Problems about words that affect other words, for example, not. It turns out that in the initial Microsoft help system, they actually put not print as a separate word for print. They actually combine not with the following word, and they use that as a word. So they actually engineered words, and you'll find out that, we'll give an example next time of some of these things that actually have 12 million words, some of these Google things, because each phrase becomes a word, and very common phrases become words in this. Problem of new words, if someone has invented a new word, you have to worry about that. So what do you do with new words? And then they get introduced because that might be important. People might not know what words to do. So there's often finds words that are new. When you find a new help page, you have to reinitiate, you have to add it in. So we have to work out how to engineer how to add these in. And then you have one help system. So this is a new language model about how this world does so how can we transfer this to a new help system? Can we use all of these things? So that's what sort of a whole lot of issues that people find for doing these things. Although I tell you although we pretend it's this nice, simple Bayes net, it's engineering it becomes much more complicated than the sort of the theories we've been looking at so far. Okay, we've got 5 minutes. All right. All right, so the last 5 minutes here, I just want to talk about this belief network. It's called a Markov chain. And we're going to look at some properties of Markov chains. So what probabilities need to be specified? Can someone just tell me? I can't see, it hurts my neck. Just a Bayes net, what needs to be specified? The probability of S0. Probability of S1 given S0. S2 given S1. S3 given S2. S4 given S3, right? There's sort of dots on the end. So it's each state given the previous ones. So we've got this. This gives us the initial conditions. In some sense, this gives us the dynamics. It tells you how from one state you get to the next state. We'll think about these as states. You can think about this. This tells us the probability of reaching this state from this state. So we're going to have a model of action, but now it's going to be like we did before for planning and things, but now it's a probabilistic model. What's the independence assumption? What independence assumptions in this? Well, let's not know. Well, the only independence assumption is everything. What was the general one? The general independence assumption. Each variable is independent of its predecessors given its parents. Right, so in fact, so tell me one, so tell me the first one you see there. Right, S2 is independent of S0 given S1. So S2 is independent of S0 given S1. What else is there? It's awful writing, isn't it? S2, what else? S3 is independent of S0 and S1 given S2. S0, S1, and S2 given S3. So in particular, Si is independent of its predecessors given Si minus 1. All right. And this is called the Markov assumption. And it conveys the fact that the state contains all the information about the history that can event future states. So in some sense, this is the definition of state that we did before. So the state here conveys all the information about the history that can affect future states. All right, let's stop there and we'll talk about play with Markov.